All right, so by the time you hear this, it should be 5:30 already because the lag time is about 6 seconds. So I'm going to get started here. What we'll do today is to go over maybe just one or two, of these three instructions of today's lab. The lab itself also contains instructions, so it's important for you not to just kind of skip the text and try to guess the right answer, because a lot of instruction is information and knowledge is actually embedded into the lab itself. All right, so I'm just debating with myself which one I should start with. I'm going to start with LDI. So LDI is an instruction, and let's see, I'm looking for the opcode table, which is here. Oh, okay, I have to sign back in again. All right, so what we'll do today is to kind of go through pretty much the whole process as what we did last Thursday, except it's going to be for a different instruction. So what we'll do is we're going to look up LDI as an instruction, which is right here. And let me zoom in just a little bit. There we go. So we can see a little bit better what it looks like. Column A, once again, is the bit pattern, the binary digit column. And it shows us that the format of the LDI instruction, as far as the opcode is concerned, is 0110, 11, and then XX. So once again, the XX, those two bits, specify which register is going to be register X in the mnemonics. We have 4 registers, and that's why we need 2 bits in order to specify one of the 4 registers. In assembly language, I call those registers just A to D, but in reality, they are numbered from 00 in binary to 11 in binary. But instead of calling register 0, register 1, which is kind of confusing because there's also 0 as a value, 1 as a value, and that is why I use A to D to designate the registers. All right, so this is column A. That's the bit pattern that the processor understands, but it's really a chore if I have to remember that 6 and then basically 6C plus the number of the register is going to be the opcode. That's going to be a chore for a human to deal with. So instead of doing that, I am using the mnemonic. So in the mnemonic, in this case, it is LDI X comma I. So we know what X is because we know that X is one of the 4 registers, A, B, C, or D. But what is I? I is an immediate value. So when I say when I use the term immediate, you can think of it as a constant. So I is just a constant. It has to be a value that is quote unquote resolvable at assemble time. In other words, the assembler must be able to resolve the actual value that is taking the place of I. It cannot be a value that is dependent on runtime behavior of the code. So that's column B, but that column B doesn't really quite tell us what this instruction is doing. What kind of pathway are we trying to establish inside the processor? So that's why we have to look at column C. Column C, once again, is expressing the operation in RTI. RTI stands for Register Transfer. RTL, sorry. I take it back. It is RTL. R is register, T is transfer, and then L is language. So that is a way in order for computer architecture people to express what is going on when an instruction executes. Okay, I saw there was a little bit of typing in Discord a little bit earlier, but I'm not seeing any text appearing. So I'm going to keep talking until I see the text here. So now we look at this notation here, and there are 2 ways to look at this. So it depends on whether you want to look at the RAM component as an array or whether you want to look at it as memory. Okay, so let me double click here so I can highlight which portion. So if you want to look at the RAM component as memory, which is the way I prefer to see it, we use this notation because it's a dereference, and then inside the dereference we have PC++, and in this case, whether it is plus plus PC or PC++ is significant because PC++ is a post-increment operation, which basically means PC does not increment until after the dereference is done. Okay, so that part is kind of important. For people who would like to look at RAM as an array, because some people may not have taken C or C++, CISP360. So this is one way to look at it, but it's not really going to circumvent the necessity to understand dereferencing or pointers and stuff like that. And over here in the comment section, I basically say star PC equals I, because what the program counter is pointing at that moment when the instruction executes is actually the constant that we are going to load into one of the registers. Column D is the English explanation of the instruction. So in this case, it says load constant value right after opcode. Okay, that sounds awfully confusing until we start to trace the actual execution of this instruction. All right, so now we want to actually inject this particular opcode and a constant into LogicSim so that we can observe, how it works. So let me bring up LogicSim again. So there we go. We have LogicSim, and there we go. I think it's good, right? Yes. All right, so let's go back to main, and we'll reset the processor. So this is also something that you might want to keep in mind is every time you're trying to test something new, it is a good idea to reset the entire circuit. So you go to simulate and you just click on reset simulation, just like that. And now simulation is reset, which also means RAM is now emptied out. Okay, so there's no actual, well, I shouldn't say, I was about to say there's no content, but there's actually content, but the content is reset to all zeros in RAM. So the first thing we need to do is to assemble the instruction. And I'm going to do it by hand just to illustrate the process. And it is also important for you guys to understand how to do this because you might get a question related to hand assembling an instruction. So let's just say that we want register B to have a value of 67 in decimal. Okay, so let me write it down because if I don't, I'm going to forget. So I'm just going to write down here and say we want register B to have a value of 67 in decimal. So this is actually the C notation of assignment. In other words, I am not asserting or testing whether register B has a value of 67. I am going to change the content of register B so that it becomes 67. Okay, so that's really important is to differentiate between single equal, which is assignment, versus double equal, which is testing for equality. So this is what we want to do, and we want to kind of find out, how the instruction does it, and we also want to find out what the opcode is. All right, so now I'm just gonna show this side by side. Because register B has a bit pattern of 0, 1 in binary because it's the quote-unquote second register. So that means the opcode is going to be 0, 110, 1101. 1101 is the letter D in hexadecimal, and 0110 is 6 in hexadecimal. So this is why I know how to put a value into RAM location 0, and we'll just go ahead. As long as you have the poking tool selected, you can click on a particular memory location in RAM if it is within the view of the component itself, and you can just type over the content that's already in it. So in this case, I'm going to type over and just type 6D on the keyboard, and now we have 6D. The interesting part about the LDI instruction is whatever byte is right after the opcode, which is 6D, is the constant that we want to put into the register that we have just specified, which is register B. And remember, I wanted to put 67 in decimal into it. So in hexadecimal, it is going to be 43. Why is it 43? Because 4 times 16 is 64. 64 plus 3 is 67. And if you're having some questions about, okay, but how does that work again? That really has to go all the way back to base conversion, because it doesn't matter what base we are using. Okay, base 2, base 10, base 7, base 16. It works exactly the same way. Each digit is telling us the quantity of a particular power of the base. So if what I just did, which is figuring out that 67 in decimal is 43 in hexadecimal, seems a little bit mysterious to you, you might want to review the content of base conversion that was, I think in week 1, week 2, maybe week 1. So that's and I think it's important to kind of bring up these reminders, because some people may have forgotten some of the content that I have introduced earlier in this summer session. All right, so we're going to put a 0, 1 in here, which is the halt instruction. The halt instruction is really just saying, okay, stop here. The program will not progress any further. So this way, if I accidentally click Control T, which is a transition of the clock line, if I accidentally click it one time too many, it's not going to do any harm. It will simply stop on byte 2. Now remember, this is byte 0, this is byte 1, this is byte 2 in memory. So I'm going to pause here and see if there are any questions. And as far as I could tell, the lag time is about 6 seconds. So I'm going to count a little bit here to make sure that you guys have enough time to ask questions. All right, so I got one person typing, so go ahead and I will wait for that question before I continue with this demonstration. Oh, we got 2 people typing. Okay, first question. 6D. 6D is coming from how I assemble the instruction. So the pattern of the instruction is in the opcode table. Oh, I think I just deleted. I just closed that tab. That's okay. So opcode table is here, and the LDI instruction description is, yeah, I wrote this and I cannot remember the positioning of the instructions. There we go. There we go. All right. So the pattern is 0110111XX. The 6 is the 10110, and then the 1101, because we need a 01 for the XX to specify register B. That is the D. That's where the D is coming from. That's why we have 6D as the opcode. All right, next question. Does resolvable at runtime include anything other than constant? So resolvable at runtime typically refer to the value of registers, because registers can change the values that they contain at runtime. Memory locations can too. Okay, so you can hack the program in a way that it is self-modifying code. So, but that's really a place that I don't want to go. So let's not assume that we are writing self-modifying code. So assuming we are not writing self-modifying code, that means the memory content, the content of memory locations corresponding to instructions, should never change during the execution of a program. So all of those locations, containing instructions and the constants for the instructions, those should be all resolvable at assemble time and not resolvable at runtime. So the only thing that should be resolvable at runtime would be content on the stack. We'll talk about that in maybe 2 more classes, and also the content in registers. I hope that answered the question. And I think Paul's question is about resolvable at compile time or assemble time and not at runtime, if I understand the question correctly. All right. Oh, okay. All right. So let's continue. Right. So continuing in the in Logisim right here. So now we are ready to run the program. And to run the program, for those of you who are totally impatient and don't want to know how the processor works, you can always go to simulate and then just enable ticking, enable ticks, or tick enabled, and just let the program run to completion and then observe that register B will end up with a value of 43 in hexadecimal. That's not going to help you very much in the next exam. So I suggest that you learn what I'm doing right now and do it to the other instructions, okay, so that you can actually find out how instructions execute and how the pathways between the components in the processor are established when we get to specific locations in the ROM. Okay, but I'm going to explain this kind of the same way as Thursday. So if you did not review the notes on Thursday, if you did not watch the video on Thursday, this is a somewhat of a repeat. Okay, but don't count on me repeating all the time. All right, so when we start, we always start with ROM because the content in ROM, which is out of the D port of the ROM component, that is what is dictating the connectivity between components, and also it also dictates what components are enabled, ready to be updated, and also how it is going to be updated. So that's why we always start here. We always start with ROM. We always look at the output of ROM so that we can figure out what is going on, what the next clock transition is going to do. So we want to look for active components. Okay, so active components would be the ones that are enabled. We can see RAM cell is a 1 because it's light green, so that means RAM is enabled. Now, as soon as you know RAM is enabled, you have to ask the next natural question that I would ask is this a read operation? Are we reading the content of a memory location? Or is this a write operation? Are we changing the content of a memory location in the next clock transition? That is answered by the LD port. If the LD, which is load, if the LD port is a 1, that means we are reading from we are reading from a location in RAM. If it is a 0, that means we are writing or changing a location in RAM. This is light green, it is a 1, so that means we are reading the content of a location in RAM. So once we know RAM is involved in this operation and we are reading from RAM, the next two questions to ask is what is specifying the address and what is using the content at the location that is addressed. So those two questions need to be answered. The first one is by tracking down the A port. So we can see the A port goes to this particular multiplexer. And I am not going to explain what a multiplexer is because that has been done already. So in this case, the multiplexer has two inputs, input 0 and input 1. And this particular select port is going to specify which input is connected to the output here. And we can see the select is light green, which means it is a 1. So that means input 1 of this multiplexer is now connected to the output of the multiplexer. So when we track this wire down, or track this net down, we can see it's coming out from the program counter. So that means the program counter, or the content of the program counter, or the value of the program counter, is dictating where in RAM we're reading from. Then the next question is, what are we doing with 6D, okay, which is now presented at the D port? How do we know 6D is presented at the D port? Just click on the wire. See, we can see 6D right here. So now we want to see, we are suspecting that some component is getting updated, because otherwise, why would we want RAM to present the content of location 0 at the D port if nobody is paying attention? So we suspect somebody is paying attention. So now we look for which component is paying attention. We can see RIEN is is a dark green, which is 0. So we know none of the registers inside the register bank is going to be updated by whatever the D port of RAM is outputting at this point. All right, so let's check out the other things. The program counter also has PCEN, the enable pin being dark green. So that means the program counter is not going to be updated. So if the program counter is not going to be updated, we don't have to, analyze it, at least not for the time being. But we can see that the instruction register does have the enable being light green. So we know the instruction register is going to update at the rising edge. And in addition to that, we also can see that the D port, the input of the instruction register, is connected to the D port of RAM right now. So whatever RAM is presenting on this node is going to be specifying how the instruction register is going to be updated when we have a rising clock. Because a rising clock is typically what register would pay attention to. Let me rephrase that. When we have a rising edge and a register is enabled, the rise at the instance of the clock transitioning from 0 to 1, that's when the register is going to be updated. So when I type Control T on the keyboard, which is causing one transition of the clock, in this case is a rising edge, the instruction register is going to update, in this case to 6D. And once again, this is called the fetch cycle. Okay, the fetch cycle is going to RAM, read the opcode in to the instruction register. That is called the fetch cycle. Control T right now, so we can see how 6D is now the content of the instruction register. The next Control T is going to be a falling edge, and only one register of the entire processor is sensitive to falling edges, and that's the microcode pointer. So the microcode pointer is always enabled. We can see how the enable line is connected to the constant of 1, which means the microcode pointer will quote-unquote change at every single falling edge. So now we want to know how is it going to be updated. So that depends on how the D port is connected. So D port is connected to the output of this multiplexer. This multiplexer is always enabled because it doesn't have a separate enable pin or separate enable port. But now we want to look at the selection. This is the select port. It is a 1. So that means input 1 is connected to the output of this particular multiplexer. Now we track down this particular net. It is coming out of the adder. This is an adder. So the adder is really just adding whatever the microcode pointer has right now at this moment and 1. That's basically what it's trying to do, is incrementing. Basically, it's incrementing by 1. And because the microcode pointer right now is 0, 0, 0, the after we perform the add, it's going to be 0, 0, 1. So when I type Control T on the keyboard, which causes a falling edge, the microcode pointer is going to become 0, 0, 1. So right here, Control T, there we go. And we can now see that the microcode pointer changes to 0, 0, 1, which also changes what location is addressed inside the ROM component. So now the ROM component has the content of location 001 presented to its own D port, which means it's time to look for components that are active, and try to figure out what is going to be changed when I type Control T, which is going to cause a rising edge in this case. So I'm going to shortcut the whole process because because I already know what is being updated. Okay, so I'm just going to go straight to the component that is updated, and that's the program counter. So the program counter is going to be updated, and every time a register is going to be updated, we want to track down what is being used to update that register. So we're going to track down this port, which is the output of this multiplexer. This multiplexer now has a dark green for its select. So that means it is going to use input 0 to connect to the output. Now we track down input 0, and it goes to a very similar mechanism. Even though this one doesn't use a constant 1, it is using a OR gate to determine whether we should be adding 1 or not. But in this case, it's definitely adding 1. So the program counter is basically going to be incremented. The program counter, let me click on somewhere else. So the program counter right now has a value of 0, 0. So that means when we click, when I type Control T is going to update to 01, because if this 00 is going into the adder is simply adding 1 to whatever the first port of the addition is specifying. So the output is just going to be 01 in this case, and we can verify that just like that by clicking on the wire. And we can also double check to make sure that that is indeed the value that the program counter is going to be updated. So we can double check on that too. So when I type Control T again, the program counter will auto increment to 01. The reason why we want to auto increment the program counter is because the opcode, which is 6D in this case, is already in the instruction register. So we don't need the program counter to be pointing to location 00 again. So that's why we are auto incrementing it. So I type Control T on the keyboard right now, and the program counter changes to 01. Then we want to find out what's going to happen next. Because the clock is high right now, it is a 1. So the next control is going to be a falling edge, and only one register changes on the falling edge, and that's the microcode pointer. So we track down the input of the microcode pointer. It is coming from the multiplexer, but this time the multiplexer has a select port or a select value of 0, which means input 0 is used to update the microcode pointer. So input 0 in this case comes from a merger, which is the reverse of a splitter, where bit 0 to bit 3 are coming from a constant of 0, and then bit 4 to bit 11 are coming from the instruction register, because we can see how this is the same tunnel. If you highlight a net or a node, it will highlight all the instances, even if they are only connected through tunnels. So we can see how the instruction register, which is an 8-bit register, is supplying for bit 4 to bit 11 to this merger, and then we have a constant of 0 supplying bit 0 to bit 3. So when we update the microcode pointer in this case, it's going to be 6D0. And we can confirm that by clicking on this net here, or this node, and it is indeed 6D0. So on the falling edge, if I type Control T, when I type Control T, the microcode pointer is going to switch to, it's going to change its value to 6D0. So once again, I said this last Thursday, and I'm going to say again, just in case people did not write it down. This is the decode cycle of executing an instruction. Okay, so this is the decode cycle. All right, Control T. And indeed, the microcode pointer is now at location 6D0. So you can probably see how the opcode that is stored in the instruction register directly changes how the microcode pointer is going to update, and is always going to go to a location that ends with a 0 as the least significant digit in base 16. That is because I was over preparing the ROM for complex instructions, so I was allowing a lot of up to 16 ROM locations per opcode, and as it turns out, I only need 1 for every instruction that I implemented. So it's basically just I'm just using more location in the ROM than I take it back. I'm allocating more locations in ROM than I actually needed. All right. So now what do we do? Well, this particular pattern here, 1D80036, that is specific to the opcode of 6D, which is LDI B with whatever immediate value. So this is controlling the pathway within the processor to accomplish what the LDI instruction is supposed to do. So now I'm going to go a little bit slower, so that we can so that you can repeat the process for other opcodes. Okay, because the idea is you should be able to repeat this process for yourself, so that you can get a better understanding of the instructions of this particular processor. So I usually start with RAM, and RAM is indeed selected, and it is a read operation. So the next thing we need to do is to find out who is specifying the address that why are we looking at location 43? Okay, that's the, no, take it back. Why are we looking at location 01, which has a content of 43? Okay, I misspoke a little bit earlier. All right, so we tracked down this net. It came from this multiplexer. The multiplexer has a select of 1, which means input 1 is used to connect to the output, and that goes to the program counter. So the program counter, once again, is controlling the address port of RAM to tell us that we want to read from location 01. And the next question is, what is going to use location 01? Because what is going to use the content at location 01? And we can see the D port is indeed outputting 43 onto this net here. And now we want to find out who is reading it, who is using the output of RAM to update itself. So in essence, we are looking for enables. Okay, we're looking for which register is enabled. The flags register is not enabled. The instruction register is not enabled. The program counter is enabled. But the question is, what is it going to be? How is it going to be updated? Because it's not necessarily updated by the data port, the D port of RAM. But we can also see RIEN is also light green, which means one of the registers inside the register bank is going to be updated. So when that is the case, we want to see, how it is going to be updated. The wire that is that's determining the value to update one of the 4 registers is coming from this multiplexer. And this particular multiplexer has a select of 0, which means input 0 is connected to the output of this multiplexer. And that is exactly what the RAM D port is connected to right now at this instant. So we know whatever this wire is being used to specify the content to update one of the registers in the register bank. The next question is now, which register is going to be updated? That is determined by RISEL, which is Register Input Select. And to gain a better view of this, it is good to right-click on the component, and then we go to View Reg Bank. So once we are here, we can see the content of reg in the input pin is 0100, which is a 4, 0011, which is a 3. So 43 is at this input pin here, and that is connected to the D port of all 4 registers. But only one of the 4 registers is going to be updated because of the decoder here. The decoder is currently enabled. There's a 1 to enable the decoder, and the select of the decoder is 01, which means output 1 of the decoder is going to be 1 and everything else is going to be 0. So we track down this wire and it is connected to register B. So as a result, register B is enabled. It is ready to be updated on the next rising edge. So this is how register B ends up with the value of 43, which is a memory location that is right after the opcode of 6D. But the story doesn't end here. Okay, so even though we can now confirm at the next rising edge, register B is going to update to 43, there's one more register that is going to be updated, which is the program counter. So now we look at the program counter. PCEN is a 1. The program counter will be updated. So now we have to track down how it is going to be updated. We look at this net. It is the output of a multiplexer. We look at the select of this multiplexer. It is a 0, so that means input 0 is used to update the program counter. And that's also coming from the adder, and it's just auto-incrementing. So the program counter is going to auto-increment. At the same time, the register B is going to be updated. And this is why we have edge-sensitive D flip-flops, because you might think that we are pulling the rug from under ourselves, because the program counter is currently used to point to a location in RAM, and the value at that location in RAM is being used to update register B, and at the same time we are incrementing the program counter. But this is actually not a problem, because it takes time. There's a propagational delay before the program counter is actually going to be updated. The content that we want to use to update the register in register B, update register B, is already at this point presented at the D port of register B. So it is not going to be a problem because the program counter takes time in order to change its output, and that in return will cause the RAM to also take time to change where it is pointing to change what location is being addressed. So by the time this D port is changed, because the program counter increments, register B inside the register bank is changed already. Okay, it's already done. So even though it looks like we are pulling the rug from under ourselves, it is not. Okay, this is actually okay. All right, so the prediction is the program counter will auto increment to 0, 2, and register B in the register bank is going to change to 4, 3 in hexadecimal when I type Control T on the keyboard. So here it goes, Control T. There we go. The program counter is now 0, 2, and the register B is also 4, 3. I made this output pin, for a few purposes, but one of the purposes is, so that we don't have to right-click and go into the register bank just to find out what is the current value of a register, because we can see this is in binary 0100, which is the 4, and then we have the 0011, which is the 3. So register B does end up with a value of 4, 3. So I'm going to pause here a little bit and see if anyone has any questions. All right, I am not seeing any questions. Well, if I'm not seeing any questions, I am going to continue because we are not done yet. We are not done yet. So the next question is, what is going to happen, with the falling edge? And I think most of you know and say, Tag, don't remind us because we know this already. Only the microcode pointer is going to update on the falling edge. Okay, but the question is, how is it going to update? So we track down the net, the input, the select of the multiplexer is a 1, so that means the input 1 of the multiplexer connects to the output, and input 1 comes from the incrementer. So we are expecting to see the microcode pointer to become 6D1, because after all, if you add 1 to 6D0, you should get 6D1. But that is not what we're going to see. Okay, so I'm going to show you what we're going to see, and then we get back to find out why is it not happening the way we thought it should happen. Okay, so here's Control T, and we go like, what? Whoa, hold on a second. We are supposed to be at 6D1. How come we got all the way back to 0, 0, 0? So the key to understand this one is to find out what is the actual bit pattern at location 6D1. So now we go right-click on the ROM component, go to Edit Content, and it presents a really huge window that, that's not helpful in our case. So I'm going to make it a little bit smaller so it fits on our screen, like so. And then we want to get to location 6D0. Alright, so here is 6D0, and this is 6D1. The processor actually ended up at location 6D1 in the ROM. It's just that as soon as it gets there, it became 0. The microcode pointer became 0. So now the question is, what is this 2 doing? Okay, it's 2 followed by 6 zeros. Why is that 2 important? Okay, so that's the question. So we want to find out which bit is corresponding to this 2. Each hexadecimal digit is corresponding to 4 bits, and we have 6 zeros here in hexadecimal. 6 times 4 is 24 bits. So that means the zeros are counting for bit 0 to bit 23. Not 24, it's bit 23 because we counted from 0. So bit 24 would have been the 1, of the 2, of the hexadecimal digit of 2. but we don't have a 1 in 2. So the 2 is actually corresponding to bit 25. Okay, so now we want to find out what is bit 25 doing in the processor. So look at this splitter here. We got bit 0, bit 1, bit 2, and so on. This is bit 25. Bit 25, now it's a 0 right now, but it was a 1 before. So that 1 is going into an OR gate, and with an OR gate, if at least one input is a 1, the output is going to be a 1. So that 1 is going to be the output, and it goes into the reset of the microcode pointer. And that is why the microcode pointer became 0. Now, you might want to say, but the ROM was actually addressing location 6D1 for a brief amount of time, and then it changed back to 0 because the register is reset. That is technically correct, but the amount of time is so short that we cannot actually see it in the simulator. Alright, so we are now back to location 000, which means we are now ready to fetch the next opcode. I'm not gonna do that because you should know already how the next opcode is going to be fetched. This is the location, and we're going to go fetch that 01 into the instruction register, decode it. Well, why don't we do that? Okay, so we'll repeat this, but this time it's going to be a little bit faster. This is the fetch cycle. Control T reads 01 into the instruction register. The falling edge is going to increment the microcode pointer to 001. And then the rising edge is going to auto increment the program counter so that the program counter would become 03 right there. And then the falling edge is going to decode this time so that what location we're going to go in the ROM is going to be oh, right. So the microcode pointer is going to be updated partially by what is in the instruction register, but it's going to pad a 0, a digit of 0 in hexadecimal on the right hand side, so that 01 becomes 010. That will be the new microcode pointer value. So Control T, there we go, 010. And at location 010 in the ROM, we just have all the zeros. So you might want to ask, what is that going to do? Well, if they're all zeros, that means no register is enabled. Because in the entire design of this processor, if you want to enable a register, it needs a 1. So a 1 is going to change all of these zeros, so you'll find something, you will find a digit that is non-zero if at least one register is enabled. And they're all disabled, right? RAM is disabled because if RAM was enabled, you will see RAM cell, which is one of the bits in here, to be a non-zero, and we're not seeing that. So nothing is enabled at this point. So if nothing is enabled, that means nothing is going to change. The program counter is not going to change, the instruction register is not going to change, and so on. So what is going to happen next? If I Control T again, the clock is 0 at this point, so when I Control T again, it's going to be a rising edge, but we know none of the registers is going to change, so when I type Control T, it is boring. Absolutely nothing happened. Now, on the falling edge, we do expect something to happen because the microcode pointer is supposed to change, because the microcode pointer is enabled connected to a constant of 1, so it's always going to change on the falling edge. The question is, how is it going to change because of the falling edge? In this case, the multiplexer that is feeding the D port of the microcode pointer has a 0. The select is a 0, which means input 0 of the multiplexer is connects to the output, and that is really just decoding the instruction register again. So we are basically decoding the same instruction over and over and over again, and as a result, it's not changing the microcode pointer. It is stuck now at location 010, and it's not going to change. It will never change from this point. So I'm just going to illustrate it. I'm going to type Control T. So Control T, when we have the clock being 1 at the time, usually would change the microcode pointer. In this case, It does change microcode pointer, but it changes microcode pointer with the same value that it already has. So there's no visible effect whatsoever because what we're using to update the microcode pointer is the value that it already has, which is the instruction register left shifted by 4 bits. So if I type Control T, you can see that absolutely nothing seems to happen, even though the microcode pointer technically is updated, except the new value, quote unquote, is the same as the old value. So there, this concludes the little demonstration and the explanation of how the processor works in the case of the LDI instruction. The LDI instruction is the only way to load a specific constant into a register. So it's really kind of important. All right, so I'm going to pause and you guys can now ask questions. You can type your question, you can use the voice channel to ask your question. I am not seeing any questions. Well, if I'm not seeing any questions, we can proceed to explain another instruction. All right. Okay. So I'm gonna introduce another instruction. Let's see, which one should I introduce next? We have been reading from RAM quite a bit already. Let's do something to write to RAM. Let's try an opcode that updates RAM. Okay, so the first question is, how do we know which opcode is going to update RAM? So the first thing we do is we go back to the opcode table. And when we are updating RAM, we should be looking for something where the dereference of something is on the left-hand side of the assignment operator. So we have to look at column C and look for something where it looks like asterisk blah blah equals to blah blah blah. Okay, that's what we are looking for. So we can, I'll just do a sequential search here. Okay, this is the no op instruction, which is open and close brace right away, which doesn't do a single thing in C. That's what the no op instruction does. This is the halt instruction. The halt instruction is an infinite loop that has no chance of exiting, and that's kind of what halt does. Is it doesn't exit. Once you get to the halt instruction, it's stuck in the halt instruction. This is a jump instruction. The register is updated on the left-hand side, but there's no dereferencing whatsoever. No dereference, no dereference, no dereference, no dereference. Da, 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 da. Keep going, keep going. Okay, you can see none of these have dereferencing until we get to this guy here. Okay, so this guy says dereference y equals to x. Okay, so in C notation, that means x is one of the 4 registers. It's the right-hand side of an assignment. It supplies the value that we're going to use to update the left-hand side. The left-hand side in this case is asterisk y, which is dereferencing register y, which basically means we're using whatever register we use to specify y to tell us which location of RAM we are going to change. So this is why it is important to have exposure to C, C++ prior to this class, because I mean this is dereferencing. Java has no dereferencing. JavaScript has no dereferencing, not the same way. Okay, it's not dereferencing a location in RAM. All right, I'm just looking at the time. Let's take row. Okay, so I'm gonna take row, and then we'll come back and find out, how to integrate this opcode into the program that we already have. And let's do something dangerous this time. So, but hold on to that thought while I go back to the row taking activity, which is not this one. And let's try this one. I cannot, there are too many tabs, I cannot remember which one is which one. All right, so let's go down to, pretty sure I made one today, unless I forget to save it. Oh, it's the other one. There we go. All right. The answer to this particular quiz is memory. I'm going to type it in the text channels. Please copy and paste. So there's no chance of a typo. So I'm going to open it up, give you guys like 5 minutes to do it. So it'll be 6:25 when it's due. July 6, 6:25 p.m. Yep, just double checking the time. There we go. So go ahead and type, copy and paste memory into the fill in the blanks quiz so that I can tell that you're here. Well, actually, I take it back so that I can tell someone signed into a particular person's account to respond to this activity. That's all I can confirm. I can't really confirm who is doing it. I'm going to assume most people have it done already. So I'm gonna open this as a new window so that I can see, how many people have responded. Then I can determine whether to proceed at this point. Yep. Okay, most people have done it, save for a few. All right, I'm going to continue it with the lecture at this point. All right, so back to the opcode table. So what we want to do is I'm going to do something dangerous, okay? Because what I'm going to do is to say asterisk A equals to C. That's what I want to do. I want to use register C to supply the value to update the memory location that register A is pointing to. All right. Yes, that meme is good. All right, so let's do it, okay? Because we are going to do something that is not supposed to be done. Even though in older processors it can be done, it's still considered something that is really dangerous, okay? Really should not do something like this, but we're going to do it. All right, so now we want to find out the opcode. The opcode pattern is 1111 XXYY. So now we have to figure out which one is register X, which is the register supplying the value, and which one is register Y, which is the register that is being used to specify where in RAM do we want to update. So to make this more specific, we know that YY is register A, which means it is the bit pattern of 0, 0. We also know XX, which is supplying the value on the right hand side, is register C, and as a bit pattern it is 1, 0. So that means the actual opcode is going to be 1111, and then the XX, which is 10, and then the YY, which is 00. So this is our opcode in binary. In hexadecimal, it is going to be F8. Okay, because 1111 is F in hexadecimal, and then 1000 is 8 in hexadecimal. All right, so we're going to go back to Logisim, and then we'll do some hacking. Okay, and I use the word or the phrase, hacking, because I'm too lazy to, put everything back in here. So I'm just going to put in the new content. Okay, so I'm going to change this one to what we have assembled earlier, which is F8. So when I use the word assemble, it really is just a translation process. It's the translation from mnemonics, which is LDI, ST, those are the mnemonics, is the translation from mnemonics into the opcode. Now, opcode is technically in binary because those are all zeros and ones. But when we represent the opcode, it's much more convenient to use hexadecimal. So it's actually in hexadecimal when we specify in RAM. And then we will put the 0, 1 over here. All right. But you would say the program is already in a halt instruction. We cannot possibly get out of the halt instruction now. That would be correct, okay? But that's also why, so to do what I'm about to do, you have to make sure the following is true first, okay? You have to make sure the clock is dark green, okay? You have to make sure clock is already 0, okay? Which it is right now. So what we do is we go all the way to the top, and here's a button called reset. So I click the button and reset the processor, and somebody's going to say, but if you reset the simulator, it's going to reset the content of RAM too. That is also true. That's also what I said earlier in class. But I did not reset the simulator. I reset only the processor because this particular net, okay, does not go to the RAM. The RAM has its own reset button here, and as a result, the content of RAM is actually retained in this case. Registers, on the other hand, are all reset because all the registers, the reset line connecting to all the registers, they're all connected to the global reset of the processor. So as I reset the processor, the registers A to D are also automatically reset. All right, so what we're going to do is to fast forward until we get to the opcode that I want to explain at this point. So I'm just going to type Control T repeatedly and carefully until F8 is selected. And I type it just one time too many. So let's find out what the microcode is doing at this point. So we have, okay, we haven't fetched yet. Okay, so we are just getting back to location 000 in ROM, which means we are ready to fetch. So right now, if I type Control T, it's the fetch cycle. And as you can see, the instruction register now has the opcode that we are about to execute coming from location 02. And then we Control T, which increments the microcode pointer. And the next Control T is going to auto increment the program counter. So the program counter will become 03. And then the next one is going to decode. Okay, so the next Control T is going to update the microcode pointer. It will take whatever we have in the instruction register, which is F8, and append a 0 to the right hand side. So it becomes F80. That is the address of the ROM where the content at that location specifies how this specific opcode is going to be implemented. In other words, it specifies the pathways between the components inside the processor to get this done. Okay, so let's Control T, get to that location, and now we ask the question, how is this done using this particular bit pattern here? So we're going to do the analysis, okay, starting with RAM. And RAM is selected, okay, but this time LD is a 0, which means we are about to update a location in RAM. So the next question is, who is specifying the address port and who's going to specify the data port? Because this time both the A port and the D port are going to be specified by something other than the RAM component itself. So we track down A port first. It comes from the multiplexer. The multiplexer says, let's connect the input to the output. So now we track down input 0. Input 0 is coming from a demultiplexer. So we check the select of the demultiplexer. It is 0. So that's good because that means the input of this demultiplexer connects to the wire that we are highlighting at this point. And now we can see it's coming out of out 1 of the register bank. Now we right click the reg bank component and click on view reg bank. So now we want to find out, okay, who is connected to this output pin here? It is coming from a multiplexer. The select of the multiplexer is 0, 0, which means input 0 connects to reg out 1. We track down that wire. It is coming out of register A. Oh, okay. So that kind of explains this part here, because now we know why register A is used to control which location is going to be updated. Okay, great. That part is explained. Now we want to find out what is connected to the D port, okay? Because in a write operation, whatever connects to the D port specifies the content of the location that is being addressed. So we click on it, and this time we only have to look for things that can drive a wire, basically just output stuff. So that means I'm not concerned about the instruction register, because this wire connects to the input of the instruction register. There's no way the instruction register can supply a content to update RAM by this kind of connection. So it's not an issue here. We are going to track it down. Let's track down this segment here. So this segment is going to the input of this multiplexer. So once again, we know the PC, the program counter, cannot possibly be specifying the content of the D port. This segment is also going to the input of a multiplexer. Once again, not an issue. So the only one that is connected to the only output that is connected to the D port right now is coming from this demultiplexer. And as a demultiplexer, we want to look at the select to find out how the input is connected to the output. We click on the select. It is a 2. So this is output 1. Excuse me. This is output 0. This is output 1. This is output 2. Okay, that's good, because this means the demultiplexer is indeed connecting the output to the D port, and it is enabled because we can see RO0EN, register output 0 enabled, is a 1. So now we want to track down this particular wire and find out how it is connected to the inside of the register bank. So right click, view reg bank. So now we are tracking down this wire. It's coming out of a multiplexer. The select of the multiplexer is 1, 0 in binary. 1, 0 in binary is 2 in decimal. This is input 0, input 1, input 2, and it connects to the output of register C. This is how we know register C is connected to the D port of RAM. And as a result, now we have just explained how we specify register C as the right-hand side of the assignment in RTL. So let's go back to the main circuit. Because remember what I said earlier, this is bad. This is something that we should not do, even if the architecture let you do it. Because what we're about to do is we're going to change location 0 from 60, which is the original opcode, to 0, 0, because register C right now has a content of 0, 0. All right, so I'm going to do a Control T right now, and the location 0, 0 is now changed. This is called self-modifying code. It's called self-modifying code because the code of the program changes itself. And it is considered extremely bad programming style to rely on self-modifying code, because self-modifying code is extremely difficult to debug. Because the program itself keeps changing, and as a result, it's very difficult to reproduce a problem. So that's why, even though the architecture in this case allows it, it's still not a very good idea. In a modern architecture, you cannot change the code segment of memory. So if you try to do that in C, C++, it's going to cause a segmentation fault, or it basically just crashes the program. The operating system will step in and go like, nah, this is not a good idea, not going to let you do it. So you don't have to worry about, accidentally making your program self-modifying in the context of a modern architecture. Basically all the Intel architecture, all the current AMD 64 architectures, they're all like that. They have protection against this kind of things from happening. So I'm just illustrating how you know, not if you're not careful, okay, in this class by using TTP, you can end up doing something like this to your program. And if you're in a loop, then you're going back to an earlier point, and the instruction that you will be executing would not be what you had in mind, in your source code, and that would make it very difficult to debug. All right, I'm gonna shut up and see if you guys have any questions. I did turn on the ultra low latency in YouTube, so the lag time is about 6 seconds right now instead of like 20 seconds. We got a question coming. That's good. Alright, so the question is, so an instruction like asterisk y equals x is not valid in those architectures. No, it's not quite that. It is just like you can do that in general, except if your y is pointing to a location of where the code is located. The processor, the memory protection mechanism of the processor, will prevent that from happening. So the instruction is allowed, okay, star y equals to x is allowed, but if y is pointing to a location that is not supposed to be updated, then it causes an exception. We call it an exception or fault, which is something that is implemented by hardware inside the processor. It causes the hardware to consult the operating system, consult the kernel, to ask the kernel, hey, is this program supposed to be able to change that location? The kernel, has a table to indicate which pages or which region of memory is changeable or writable. And if it comes back as, nope, this location is not writable, then it will cause an interrupt to happen. And at which point the operating system will say, okay, this is an exception or segmentation fault, depending on how you want to call that, and the program basically crashes at that point. Yep. Okay. Cool. Any other questions? No other questions. I'm looking at the time. It is 6:36, almost 37 right now. If there are no questions, I can do another opcode, which is the LD instruction. All right, let's do that. All right, so the next instruction is called the LD instruction. Well, let me see. Let me instead talk about the concept of a label, because I think that is also something that is kind of useful and important. So I'm instead using explaining the concept of a label. All right, so to understand why there are labels, I'm going to go back to the assembler and go to the source tab of the assembler. All right. There are two concepts that are kind of important here. One is it's not an instruction. This is called a directive, which is byte. Okay, so it really is just byte as a word, and whatever value you want this particular byte to have. So I know it sounds confusing, but I'm gonna specify this at this point. And the value that you can use to specify the value of this byte location in memory, you can use postfix notation, which is it's better to show you than to have to explain it to you. Remember the 6D? Okay, 6D is 13 plus, okay, I'm going to use infix notation, and then I'll change it to postfix notation. So it's 13, which is the D, plus 16 times 6. Oops, I said 16 and I typed 15. So this in decimal specifies the value of the hexadecimal value of 6D. So this is using infix notation. Infix notation basically means you have the operator between the operands. Postfix notation is exactly what the name implies. The operator is right after the value that you want to work on. So the way to specify the postfix notation is you put 13 here, but you're not going to do anything with 13 yet because we have to perform the multiplication of 16 and 6. And the plus goes here. So the way we read this is we see 13 and then we say, well, we don't know what to do with the 13. Let's just, stash it somewhere. And then we encounter the 16, same thing, we don't know what to do with the 16, stash it somewhere on top of the 13. And then we see the 6, once again, don't know what to do with it, and we just say, gonna stash it on top of the 16. So now we have 13, 16, and 6, stacked up in that particular order. And what the multiplication operator is going to do is to say, okay, I'm going to take two things off of that stash and multiply those two things. So it's going to take the 6 off because it's on top of the stash, and then it's going to take the 16, which is the second item, on the stash. So take off those two items, multiply those two, which will give us what? 6 times 16 is 96, right? So it will give us 96. So the question is, where do we put that 96? Put it back on the stash. So we take two items off of the stash, calculate, put the result back on the stash. So after the asterisk is processed, then we will have 13 and 96 on the stash. And then we encounter the plus, which is basically saying, you probably guessed, we take off two items from the stash, which is 13 and 96 at this point, perform the addition, which is 13 plus 96, which is what? 109, and then put that back onto the stash. So the last item that ends up on the stash is 109. Okay, so we'll stash it here. And then the next one is going to be 43 in hexadecimal, which is our 67. I might as well just use 67 here. And then we're going to use the, what was I about to say? Right. Okay, so let's put the LD instruction now. All right, so we're going to use the LD instruction. The LD instruction, oh, I just did something right there. Okay, there we go. So the LD instruction looks like the ST instruction, except everything is backwards. So we use the first operand to specify which register specifies the location to read from. So in this case, I'm going to use, let's see, we put that into register B. So we want to use register B to tell me where in memory to read from. And then the second one, oh, I take it back. Actually, I take it back. It's the first one is which register to be updated, and then the second one specifies where in memory do we want to get the content to update register A. So if you look up the opcode table, the LD instruction is here. And you can see how it is the exact opposite of the ST instruction, where star asterisk Y is the right hand side because we are reading from a location in RAM using register Y, and we're going to use the content at that location to update register X. So it's the exact opposite of the other one. And so now we want to halt instruction here. All right. So now you can also use the byte directive to specify, the content of a location. So I can just arbitrarily say, okay, I want to put the content of 113 here. And if I want the instruction, the LDI instruction combined with the LD instruction to read this 113 into register A, then I have to do some counting, right? In other words, this 67 should not be 67 anymore. It should be the location of this byte here. Now, it is also helpful to switch to the Assemble tab, because in the Assemble tab, we can now see what is in the content of memory. At location 0, we have the content of, okay, I think it's better for me to use the keyboard to do this. So at location 00 in hexadecimal, we have 6D as its content. Then you go like, but isn't 6D the same thing as LDI, and then use register B, and update to register B? Exactly. So we can specify the content, in various ways. Okay, so we can actually hand calculate the opcode and then just plug it in like this. The next location specifies the constant, which is 643 in hexadecimal. That's something that we talked about before. So if you look at the first two bytes, byte 0 and byte 1 of the program at this point, that's exactly what we had before my program self-modified and changed location 00. So, yep, that's one way to do it. But if I want the LD instruction to read from this location, so now I have to look at the assemble view and say, oh, okay, we want to read from location 04, so that's why we want to use 4 instead of 67 at this location. So that you can do that, okay, because the constant of 113 is at location 04 when we look at the assemble view. But that means if you insert any instruction here, that's going to change the offset of where this byte 113 is located. And the way to make this easier is to make use of a label. So the use of a label means, right before the line that specifies the byte that I want to read from, or the address of that byte is important to me, I will define the label. So I'm going to define the label of L1 in this case. Now, you can use any C identifier syntax to specify a label. So you can use underscore, uppercase, lowercase. Everything is going to be converted to the same case, so it's not case sensitive. But you can use alphanumeric for label names. So now when we look at the assemble tab, nothing has changed. Okay, you can see the bytes are at exactly the same location as they are. But you can also see a label L1 is defined to 4 in this case. So when we need to refer to the location of this byte 113 in the source code, instead of having me to have to manually keep track of where that location is, I can now refer to the symbolic name, which is L1. So this is one of the purposes of having labels, is having a label allows us to associate a symbolic name with whatever is at the location when the label is defined. The assemble tab is really helpful to illustrate what that concept means, because we can see how the assembler is using consecutive memory locations. The 6D is location 0, the 04 is location 1, this is location 2, location 3, this is location 4. So as far as the assembler is concerned, the more instruction you add, it will just continue to use consecutive locations, in memory. And the purpose of the label is to remember up to where in memory we have used at the time of the label. And as a result, whatever we define right after is going to have the address of whatever is defined right after is going to be the value of the label. I'm not really sure whether that explains well or not. Yet another tab that you might find helpful for those of you who want to kind of look deeper into this is the SymTab tab. SymTab tab, is not redundant because the first tab is the abbreviation of table, because this is the symbol table, and then the second tab refers to the actual tab in the spreadsheet. So in here, we can see L1 is defined on line 4, and it is defined to the address of 4. So that's the other way to look at how a label is defined, is to look up the symbol table. The explanation of a label is actually in today's lab. Okay, so if you don't quite get what I'm saying, the lab instruction of today's exercise actually has that explanation as well. All right, I'm looking at questions. Oh, okay. I forgot. I didn't read that part. But I thought the labels are more important to explain. All right, so I'm about to run out of time. And one ungraded assignment I want you guys to do is to do exactly what I did. Uh, using Control T to cause the transitions. And this time I want you to track the execution of an LD instruction, so that way this gives you an opportunity to get some hands-on exercise to track down how the processor works. Okay, it's the same process as what I did twice today and one time last Thursday, but on a different instructions. So that hopefully that will give you an idea of how to quote unquote study from this point on. All right, so I'm out of time, and I'm going to release the lab for tonight. Of course, I lost track of all the tabs. All right, so the lab tonight is titled LD, ST, and LDI. You cannot see it yet. I have to release it first. All right, so it does allow multiple attempts. The access code is just LDI. Okay, so I'm going to type it in the text channel. So LDI is the access code of tonight's lab, and it's going to do at the usual time of 8:20 p.m. There we go. And save and publish. All right. So I'm going to take a short break, and I'll be back in about 10 minutes. And remember, don't try to rush through the lab, okay? Because the lab itself contains instructions. It contains explanations of what labels are. And if you're concerned about the lab may not be viewable, so that you cannot review the content, you can always take screenshots or print it. There are tons of ways to copy the content of the quiz to your own resource, so that way you can always review the instruction of a lab even when the lab itself is not open. All right, so I'm gonna walk away for about 10 minutes, and I'll be back.